this new Severo colloquium that exceptionally is taking place on Friday instead of the day before. It's a pleasure for us today to have Dr. Roberta Fanin. Thank you very much, Roberta, for having accepted our invitation for this colloquium. Dr. Roberta Fanin studied physics at the University of Padova in Italy, and during her PhD at the Institut de Física d'Altes Energies in Barcelona, if it's said properly, she performed a very high emission gamma ray characterization of the emission of the Crab Nebula that she completed in 2011. Then she worked as a Juan de la Cierva Fellow at the Universidad de Barcelona, where she also studied the high energy emission of the Crab pulsar. Then she moved in 2015 to the Max Planck Institute in Heidelberg to work as a postdoc, studying pulsar, wind, nebulae, and microquasars. Since 2019, she's the project scientist in the Cherenkov Telescope Array Observatory, CTAO, in Bologna. As such, she has a key role in all science-related aspects of the CTA construction and operation. Roberta works with the project manager and the system engineers in tandem with the in-kind contributors and the CTA consortium to ensure, of course, that the design, implementation, and science verification of CTA achieves the science goals of the project. She's also a member of the CTAO Change Control Board, of course. And today, as you know, she's speaking about the use of CTAO for cosmic ray physics. So thanks again, Roberta, and the board is yours.
Thank you for the kind introduction. And it's a pleasure actually to be here with you. So when Ruben invited me, he was making me aware that you had another speaker a few months ago, really talking about the Cherenkov Telescope Array Observatory, so introducing the technique, the detection technique behind. So then I thought, okay, so let's skip that part, so the audience is already well aware of these basic principles, and we go directly into one specific science topic. And I hope that the cosmic ray physics could be of your interest, given what at least I know are the interests of these institutes. So for this reason, No?
No, sorry.
Okay, now it works. Okay, so the idea of the talk is to have a really short introduction on cosmic rays and their link to gamma rays. So why are we talking about cosmic ray physics if the Cherenkov Telescope Array Observatory is actually a gamma ray facilities? So there is a short introduction as a parenthesis on the gamma ray astronomy. So which are the facilities, which are the capabilities, so which are the performance parameters that we need to actually carry out the studies on cosmic ray physics related questions, and then we dive into really the cosmic ray physics. So what we can do with gamma rays in terms of cosmic ray physics. So we start with this very famous plot that any of us has seen. So this is the spectrum of the cosmic rays. So these charged particles that arrive to the Earth, and they are mainly protons, but there are other particles. So certainly the protons are the dominant one. So if we look at the whole particle spectrum, this is dominated by the proton emission. The whole particle spectrum has a power law, so it extends over several decays in energy, and has a power law spectrum with a photon index of minus 2.7 until a certain point, then it starts to steepen. So this certain point is one of the key features of the cosmic ray spectrum, and it's called the knee. So why is it relevant, and especially relevant for the talk of today, is because it is believed, I mean, that the cosmic rays in the before the knees, so for the energies below the knee, so here in these energy range, they are produced by galactic sources. So they are of galactic origins. The reasoning behind is that the largest radius of these particles, which is about 10 to 12 centimeters, then it's much smaller than any length scale, galactic length scales. So basically, we know that up to here, so the cosmic rays are produced somewhere within our galaxies. So the energy density that we can measure in the local universe, where we mean really in the close to the solar system, is this value here. So it's 1 electron volt over cube centimeter. And this is basically equal to the energy density of the magnetic fields and the soft photon backgrounds that we have in our environment, so in close to the solar systems. So then one can translate this density into the total energy, and one can also compute the power that needs to be injected by these sources that are producing cosmic rays, by assuming a residence time, which is about a few mega years. So, and these numbers that we will come back to it is about 10 to 14 erg over seconds. So this is basically the short overview on the cosmic rays. Yeah, so this is, as I said, so these are of galactic. So we concentrate on the cosmic rays, let's say up to PV energies, where there is this knee feature, and so these are the galactic cosmic rays. So there are two main questions related to cosmic rays that we can try to tackle, and they are related to where these cosmic rays are produced and where these cosmic rays, how these cosmic rays propagate in our galaxy. So these are, there's one important, basic point is that these are charged particles, so they do not they do not travel linearly, and because they are deflected by the intergalactic interstellar magnetic field. So this means that they do not carry with them the information on the source position. So we cannot really understand which is the source of the cosmic rays just by looking at cosmic rays directly, because we lose that directional information because of the deflection with the magnetic field. These charged particles then are deflected into the interstellar magnetic field. They propagate in our galaxy. They have this residence time, as we said, of about 10 to 7 years, and they diffuse. They mainly diffuse within these magnetic galactic center, galactic halos. So the point here is that they diffuse in a region, and they are trapped in a region which is larger than the galactic disk. It's what we call the galactic halo. And there the diffusion, the average diffusion coefficient is about 3 times 10 to 28 square centimeters over second. So I give these numbers because we come back to these numbers later, and these are like the basic, really basic numbers. So now what we want is really to try to understand where these are produced, so which translates into which are the what we call the cosmic accelerators, and how do they travel in our galaxy, how do they diffuse in our galaxy, so how do they propagate. And as I said, we cannot rely on the direct detection of the cosmic rays, mainly for the reason that they do not carry special information. But here there is a process that helps us to really understand, to really answer this question. And it's the fact that the cosmic rays, so mainly protons, interact with interstellar gas. And as such, so they produce pions, either charged or neutral. Neutral pions decay into gamma-gamma, so they produce gamma rays, where more or less, to give you a rough idea, so the energy of the produced gamma under this mechanism are a factor 10 smaller than the original and the energy of the original proton. On the other hand, if we have charged pions, they produce neutrinos. And both gamma rays and neutrinos are neutral particles that they do keep spatial information. So if we look now at in gamma rays, we can try to indirectly reconstruct where they come from. So we can really see where these we can reconstruct where these gammas interacted with the gas. And if it is close enough to the region where these cosmic rays are accelerated, then we also know where the cosmic rays are produced. There is a big but in all these, is that there are also electrons up there, and the electrons produce gamma rays as well. They produce gamma rays either via synchrotron, inverse Compton, or Bremsstrahlung, and they produce gamma rays in a very efficient way. So when we do detect a gamma ray source, it's not by definition that this is a cosmic ray accelerator. We first need to understand if this emission comes from what we call hadronic origin, so it's related to the cosmic rays, or if it is purely leptonic mechanism, so that it's produced by electrons. So this is an extra difficulty that we have when we want to really answer the question where the cosmic rays are produced. So what we can do by using the gamma rays are, on one hand, as I was just saying, looking at discrete sources, so really individual sources. And in this way, we can not only identify the region where these are produced, but also study the acceleration mechanism to some extent. But we can also look at the diffuse emission. We will talk in detail later in this talk what the diffuse emission is. But basically, the idea is that you have all these cosmic rays, these protons in our galaxy, they interact with the existing gas along the galactic plane, and they produce a large-scale structure emission that you can detect in gamma rays. And then if you saw the first image, this is a Fermi-Lat image, so in the energy range of, let's say, 100 MeV, and you see that the diffuse emission is indeed the most dominant component in this energy range. And the diffuse emission can really provide inputs on the spatial distribution of cosmic rays. I said before that we can directly measure the cosmic rays in the vicinity of the solar system. There are also measurements at the edges of the solar system. But how do I know that the cosmic rays density is exactly the same here close to us and across the entire galaxy? So by looking at diffuse emission, and not only, but we will see it later, we can really try to understand what's the spatial distribution and how then cosmic rays propagate. So we pause a second before going into the details of the cosmic ray physics through the gamma ray astronomy on gamma ray astronomy. So this is what in principle you have been talked by the previous speaker on that you had on the gamma ray astronomy, very high energy astronomy. So gamma rays start at around 500 TeV, but sorry, 0.5 MeV, yes. So but then they extend over several decays in energies. So since they cover a large range of energies, they are split into different sub-energy ranges, and each of which has its own detection technique. So we have for this talk, what is relevant is the high energy range, which is between, let's say, 100 of MeV, 100 of GeV, and the very high energy range, which is above 100 of GeVs up to hundreds of TeV. Here, there is also another energy range that is popping up recently, which is the ultra high energy that goes at energies above hundreds of TeV. So the high energy range is what to look at this in this range. We do have satellites. So the atmosphere the Earth's atmosphere is not transparent to gamma rays. So if we want to directly detect them, we need to have spaceborne instruments. So the currently existing ones are Fermi-LAT and Agile. So they are conversion pair telescopes with a detection area of about 1 square meter. So this is really the limiting factor in terms of maximum energy that you want to reach. So then if you want to really go to the highest energies, you can, of course, integrate as much as possible, so as much time as possible with this instrument, but you will reach the TeV energy. The TeV energy is not much more than this. So if we really want to explore the very high energy range, what we need are ground-based telescopes that have a larger collection area and then can reach the highest energies. So here, as I said, the Earth atmosphere is not transparent, so we cannot directly detect gamma rays, but indeed we can indirectly detect them by looking at the secondary particles that these gamma rays produce when enter the Earth atmosphere. So they produce what we call the extensive air showers, and these are charged particles that can be detected from ground with for instance, particle shower detector like Hawk here, but you can also detect them with the imaging atmospheric Cherenkov telescopes, so like arrays of IACTs that do not directly detect the charged particles of these secondary charged particles, but they detect the Cherenkov light that these charged particles produce while traveling through the atmosphere at a velocity which is larger than the speed of the light in the medium. So it's a double indirect detection. So we do detect Cherenkov light, which is visible light. So these are like optical telescopes that detect the Cherenkov light produced by the showers that is produced by the interaction of the primary gamma rays with some molecules of the air. So in this way, it looks very complex, but now the technique is really mature enough that we can estimate the energy and the direction of the primary gamma rays. So at the moment, there are three facilities of this kind of IACTs that are running. So MAGIC, which is in La Palma, where you have a group here in your institute participating to this collaboration, Veritas in Arizona, and HES in Namibia. And for the particle showers arrays that are instead detecting so these are tanks of waters where the charged particles enters, and then when it enters into the water produce Cherenkov light, and this is what is captured by the PMT that is at the basis of the tank. So the currently existing instrument of this kind is Hawk in Mexico. And there is another instrument that has started to run in the last years, which is LASO, and we will talk in a second about this. So this to say which are the facilities that we have. We will see which are the facilities that we have now, and we will see the facility that we will have in the close futures to really cover the high energy and the very high energy ranges. So the gamma ray astronomy really underwent, we can say, a revolution in the last decades. And so this is the situation of the gamma ray astronomy here on the top. So you have high energies and very high energy here in the 90s. So we had the 30 grid catalog with 200 sources, and then we had the 3 sources known, in the very high energies. Now, after the advent of Fermi-LAT and of the 3 imaging atmospheric Cherenkov telescopes array that I mentioned, so HESS, Veritas, and HESS, these numbers has increased by a factor, 2 orders of magnitude. So we have more than 4,000 sources here in the high energies and more than 200 sources in the very high energy. So really now we have information, we have data that can help us in really answering the physical questions that we want to pose. So now we saw basically that we have instruments that are capable, I mean, that are successfully in the gamma ray astronomy, and there are two future instruments that I want to mention. One is CTAO, so the Cherenkov Telescope Array Observatory. So this is the next generation of array of ICTs that will have two array sites. One is in the northern hemisphere, the same site as MAGIC. And you have one of the group, your group here is actually working on the development of one of the largest telescope on this site. And then the other site on the southern array is in Isoland in Paranal in Chile. So this is from the point of view of the IACT arrays. From the point of view of particle shower detectors, there is LASO, which is an instrument that has become operational 3 years ago. So this is really a particle shower detector with plenty of, so there are more than 5,000 scintillators that are and between them, there are muon detectors that allow us to detect the muons. So these are tanks of waters under the ground that can detect the Cherenkov light produced by muons, and this allows to improve the background rejection of the instrument. And you see that in the middle you have the water pond that follow the same principle as OAK as I was mentioning. So these instruments that have a much larger collection area, so they are talking about square kilometers, so can really reach the highest energies. Then there is another instrument at the horizon, but it's not yet funded, which is called SWGO, so Southern Wide Field of View Gamma Ray Observatory, which is basically follows the same principle as HAWK, but is foreseen to be in the southern array. So the one we talk about, I always made this distinction, but I want to point out that the distinction between these two kinds of facilities that are sharing the same energy range, or at least they have an overlap in the energy range, but there are few differences that are relevant to understand. So first of all, the arrays of IACTs have a lower energy threshold, so they can reach the GeV, the tens of GeV, so they can overlap with the Fermi-Lat data, and they can extend up to hundreds of TeV. Whereas the particle shower detector depends very much on the height of the site, but they, I mean, it's difficult that they reach the hundreds of GeV. Then there is also a difference in the duty cycle. So the Cherenkov Telescope Array, the IACT arrays, as I said, are optical telescopes. So they observe in the night. So their duty cycle is limited to the dark time, whereas the others observe 24 hours a day. And also the field of view is very different. So these are pointing instruments with up to 10 degrees field of view. The other ones are not pointing instruments, so they look at the sky and they see more or less 2/3 of the sky in 24 hours. So these are basic information and difference between the two. The other important difference is related to the performance of these two kinds of facilities. So here you have the sensitivity, so the minimum flux on which you can detect a source as a function of the energy. So this is, okay, so you have here in black and red the sensitivity for the southern and northern CTA arrays, but you see here in purples, which is the sensitivity. So this works when you want. The sensitivity of the MAGIC, so the currently running facility of the same kind. And what I think is relevant is to compare with, for instance, with LASO. So you see that up to tens of TeV, the ICT arrays can be competitive with the particle shower detectors, but this is not anymore to once you go at the highest energies, and this is related to really the dimension of the collection area. So here at the highest energies, if we want to look at hundreds of TeV, then the particle array detectors are indeed overperforming with respect to the IACT arrays. Of course, the sensitivity is not the only important parameter. We also have the angular resolution. And here you see, I don't have, unfortunately, the curve for LASO, but you see here the OC1 as a reference for the particle shower detectors compared with the Veritas, so like ICT arrays, current generation and future generation. And you see here that there is almost an order of magnitude of difference. So this translates that the resolving power of these two kind of facility is very different. So when we need precision studies, then IACT is what you want to use in terms of both angular and energy resolution. Once you want instead to have a fast survey and to pinpoint where the photons are coming from, certainly at the highest energies, the particle array detectors are more efficient. So to say these two kind of facilities are really complementary, and we should try to profit from to benefit and profit from the existence of these two different facilities to get the best of the science we want to reach. Okay, so with all this in mind, we go to the first initial question, which is where the cosmic rays are produced. So we know that they are galactic, so that we want to dig into the gamma rays, so emitting sources in our galaxy, and to see which are the potential sites. So the first idea that is as old as beginning of the 20th century is that the supernova remnants are the sources of the cosmic rays. So this actually, the reason for this is twofold. On one hand, so the energetics is really what you expect, and you can recover the 10 to 41 erg per second that I mentioned before with the rate of supernova explosion of 3 per century, and assuming a 10% efficiency of the released energies of one supernova explosion. So the energetic works, and on the other hand, we know that there are supernova shocks that are very efficient in accelerating particles, and this is all justified by the DSA, so diffuse shock acceleration mechanism, and just by and a 10% efficiency is what you usually use in the theoretical calculation of this kind of work. So really, we have a mechanism that can indeed explain the particle acceleration, and we have the energetic. We know that under these scenarios, the maximum energy of the accelerated particles is proportional to the shock speed, and we do expect a particle spectrum of about e to minus 2, so quite a hard spectrum. So the first really, I mean, this was believed for many, many years that the supernova remnants are indeed a source of cosmic rays, but the really smoking gun came with Agile and Fermilat that begin more or less 10 years ago. They detect what we call in jargon the pion bump, so from the middle age supernova remnants. So these are middle-aged supernova remnants where you do see that this is the spectrum of 2 of them, and you see that there is a rapid turnover at around a few hundred of MeV, and this is exactly what we call as pion bump. So this is related to the fact that it's the mass of the pion, and the spectrum in the rest frame should peak at 70 MeV, but then when you go into the observer frame, this translates to these energies around hundreds of MeV. So you see here for these two initial discovery sources where you have the pion, the hadronic model compared to, this is the leptonic model from Bremsstrahlung emission, and the data really favors the hadronic with the pion bump that I was mentioned. So after this discovery, many different teams has looked into all the supernova remnants and middle-age supernova remnants to look for the same kind of feature. And this was found here. You have two others, but there are many more than this. So these are, sorry, I didn't, so if you look at the spectrum here, you see that the spectrum of these sources, so these are quite old sources, so tens of thousands of years, and this spectrum is fading away at around some tens of GeV. So it's indeed, they are sources of cosmic rays, but they cannot be the sources of cosmic rays up to the highest energies. We said before that the knee of the cosmic ray spectrum is around PeV energies. So we do need to look for sources that are able to accelerate particles up to these energies. And this would translate into looking in gamma rays at hundreds of TeV. So it's clear that middle-age supernova remnants confirm that they are indeed cosmic ray accelerators, but they cannot be the most extreme cosmic ray accelerators, which is what we call the pevatrons. So those sources that are able to accelerate particles up to PeV energies. So then when we So then the first thing you can think about is, instead of looking to middle-age supernova remnant, I look for young supernova remnants. So in young supernova remnants, the speed of the shock is much higher. So we are talking about the tens of thousands of kilometers per second. And so they should be able to accelerate particles up to the highest energies. And this is a plot, so a summary plot that was published a few years ago, where you see the spectrum of the young supernova remnants that have been detected at very high energy so far. And you see here two striking things. One is that this is, so all of them basically are fading away at tens of TeV. So this can be a matter of statistics, so the sensitivity limit of the current generation. But it's also striking that these specs are not very hard, as one would expect from the DSA, the diffuse shock acceleration mechanism, but they are indeed steeper. And the other important point is that, so we have all these nice spectra, many of them are really precision measurements with statistic errors quite small. And but then the question is, are these spectra produced? Are we sure that these spectra are produced by proton interaction and are not of leptonic origins? So what we usually do is to try to fit the spectral point with both a leptonic and an hadronic mechanism model. And you do see here that despite the precision of the measurements, we cannot really disentangle between the two models. So it's really hard, even for the brightest sources, to be able to discriminate what's the model and to say I'm sure that these come from the hadronic mechanism. Here, it's also worth to mention that you see the band of the systematic uncertainty that are quite large still for these facilities, and this doesn't help, of course, in this kind of precision study. So sometimes, even though the spectral measurements are not good enough or are not able to shed light on this specific topic, we can use spatial studies, so morphology study. Here you see this is the same source as before. This is one of the brightest supernova remnants seen from the southern sky, RSJ 1713. And you see here, this is the Hess sky map overlaid with the radio contours. So it really resembles very well the shell of the supernova remnant, and this was split into 5 sectors, and per sector, starting from the center of the shell, we have produced the profile. And you see here, so this is the profile of one of the sectors, and it's overlaid with XMM Newton profile. So these are X-rays compared to gamma rays. And you see that the gamma ray extension is larger than the X-rays. So this is telling us, so the X-rays that are freshly accelerated electrons, they are coincident with the shell. And this measurement is telling you that the gamma rays instead have, some of them have left the shell and are illuminating, so a region around the shell. And this can be done in the hadronic scenario only, where you know that the cosmic rays can escape the source, and the highest the energy is, the fastest is the escape. So this was a hint this result was hinting to the hadronic emission of these supernova. So I said before that there is a problem with the steepness of these spectra. So even if we assume that these are of hadronic origin, so these are cosmic ray accelerators, we do have spectra that are too steep, that are in the range between 2.4 and 2.7. So there are different interpretations. I have summarized the 3 of them here. So on one hand, you can say, okay, so this is the hard spectrum as you expect, plus an exponential cutoff that I cannot measure because of the instrumental limitations. So with future instrument, I can indeed resolve these problems. And in this scenario, young supernova remnant would not be able to be the pevotons, so the extreme cosmic ray accelerators, because we saw already that this is fading away before hundreds of TeV. There are different theoretical models that are now trying to explain steep power law spectra in specific environments, and this can extend to 1 PV. So if we dig into theory, there are possible explanations. And we can also assume that the PeV phase of one supernova remnant lasts just for the early phases of their life, so around hundreds of years, when the shock speed is still high enough to accelerate particles up to the PeV energies. So if this is the case, then what we would need to do is, instead of looking at the supernova remnant spectrum, we should be looking at the cosmic rays that have escaped the shell, and the emission that these escaped cosmic rays can produce. So if we now look into these scenarios where we are looking for escaped cosmic rays, what we are looking for is illuminated molecular clouds. So the principle is that you have particles here produced accelerated into the shocks, that this is the shock, and then they escape and they propagate into the interstellar medium until they find what we call the molecular cloud, so high density gas. And then there, what happens is that the cosmic rays, so the protons, interact with the gas and produce gamma rays. So this produce an enhanced emission in gamma rays. And these are clouds, we call it illuminated, because are illuminated by cosmic rays that are recently accelerated and escaped from the supernova. So here, I go a little bit faster here. So what you expect to see is on the spectrum of these illuminated molecular clouds, you would expect to see a feature like this one. So you start to see not only the cosmic ray steady spectrum, which would be this one, but also a new bump. And this new bump depends on the distance between the molecular clouds and the source, and also by the age of the source. These kind of things, you see that this bump happens around 100 of GeV. So this is something that certainly IACT arrays can do. And a future experiments with a better energy resolution can indeed resolve these kind of spectral features. Okay, so when we look to these kind of features, we can also get the help of the multi-wavelengths, in the sense that we know that the secondary electrons produced in proton-proton interaction can produce hard X-ray emission. So you can see the same kind of bump also in hard X-rays. So this alone would be a smoking gun for the detection of the illuminated clouds, but we can also use this one as another smoking gun for the detection of illuminated clouds. So this, just to say that we have been detecting this kind of illuminated clouds already. So this is the first results of this kind. It's one of the middle-age supernova remnants. You see here the sky map by Hess. So this is the shell, the expected shell, and Hess is only detected at very high energy, one part of the shell. And there are three sources that are appearing really close by, and these are in good correlation with high gas density. So this was the first hint of a detection of high energy cosmic rays that have left escaped the shell. We also looked, now we have several of these kind of examples. So here the statistics is too small. So these are results at 5 sigma level. So we cannot really say anything from the spectral point of view. We do need much more precision, both in terms of angular resolution and energy and statistics, also more sensitivity to be able to really look at the smoking gun features I was mentioning before. So here, this is another example. So this is W44, another middle-age supernova remnant. You see that two sources are appearing right outside the shell, which is the oval there. What is interesting there is that these sources do not coincide with high gas density. So here the interpretation is that in this case, this enhanced gamma ray emission doesn't come from the gas, from the enhancement of the gas, but from the enhancement of cosmic rays. So this means that the cosmic rays that are escaping in a specific direction, which is the one aligned with the magnetic field. So it's not just to say, this is just as an example to say that it's not as easy as if I detect a small sources close by to the supernova remnant, I know that this is an illuminated clouds. So there can be interpretation. That's why it's really important to collect the great most of the results and precision results to be able to tackle this kind of problems. So I want to mention also that, as I said, so there was LASO and OAK that came online in the last years, and these sources, these kind of facilities really helped in identified the positions in our galaxy where with significant emission above 50 or 100 of TeV. And so the first things that we thought when we saw this kind of map said, okay, so now we have plenty of pevatons, because if you assume that you are looking emission above 100 TeV, then you know that if it is leptonic, there is the Klein-Shiner regime that is really steepening the spectra. So then naive, at the first approximation, you say these are all pevatons. Then you start to dig into the problem and to make some numbers. This was a nice paper that Ruben has published last year that is proven that the leptonic emission of all the all these laser sources is still, the emission of the laser sources that I have just shown is still compatible with leptonic emissions, and this is still consistent with the pulsar potential drop. So you see here all the sources, and the only sources that are all below this pulsar potential drop. The only sources that is outside is this one, which is a star-forming region, so the Cygnus cocoon. And so the Cygnus cocoon is an interesting source. So there was another study same year that tried to look for the pion bump in a systematic way in all the sources of the Fermi-Lat catalog. And they showed that, so the result of this is that they found 15 sources with the pion bump, with significant pion bump. So 13 of them are supernova remnants, 4 of them are binaries, but one of them is a star-forming region, and it is the Cygnus cocoon. So again, the Cygnus cocoon looks like a source of cosmic rays. And we know that this is a star-forming region. So now, basically, the idea is that young stellar clusters, so the young stellar cluster could indeed be the sources of cosmic rays. So this was an old idea, as old as 1983 from Katrin Cesarski and Mommel, that they claimed that even though the speed of the wind is much smaller than what you can get in a supernova remnant, then you can still accelerated particles up to PeV energies, thanks to the fact that here the integration time is much longer, because here you can integrate for 10 to 6 years. So they also show that the gamma ray has been detected in several systems with a hard spectrum, so harder than what I mentioned before for the supernova remnants. And what is interesting is that we have started to produce the projection, so the profile, the density of the cosmic ray as a function of the distance. And you see that the profile looks like it's well fitted by 1 over R. 1 over R density profile means that there is a continuum injection of the stellar cluster for about, as I said, 10 to 6 years. So here I want to mention, so this is one of the sources that I mentioned is the Cygnus cocoon. There was last year the paper from Hook that showed not only the Fermi-Lat point on which the results that I just shown on 1 over R was based, but also the new TV measurements. And what is interesting here is that they did the same exercise. So they compute the projection of the cosmic ray density. And you see in black the points I have just shown, and in green the new, so these are high energies, and in green very high energies from Hawk. And you see here that with the Hawk data, you cannot really, you cannot exclude the constant profile. A constant profile would translate into a burst injection. So here there is something that is not yet understood, and more data are definitely needed to try to answer this question. There is also the possibility that since the TV's energy, the cosmic ray escape, then this kind of profile that becomes, let's say, more constant and less 1 over R because of the escape of the highest energies cosmic rays. Okay, so I go faster, a little really faster, 5 minutes on the diffuse emission. So the diffuse emission, as I said before, so it's the pion decay process from proton interaction plus inverse Compton and Bremsstrahlung of relativistic electrons. So if you accumulate and mixture all these particles, so convection and diffusion, what you have is what we call the cosmic ray sea that is permeating the entire galaxy. So you would expect that this is homogeneous on kiloparsec scales. And what we want to study is really if we can, with the data we have in gamma rays, we can say something. So the idea is that the cosmic ray density is proportional to the gamma ray flux and also depends on the column density of the gas. So if I know the radio and I know the gamma, I have good radio data and good gamma data, then I can derive the cosmic ray density. So this has been done extensively with the Fermi-Lat data. And the first result is that so they tried to split our galaxy into galactocentric rings. So they have the galactic center at the center, and then to define several rings. So these, of course, you are assuming in this way you are assuming cylindric symmetries. But they tried to measure so the cosmic ray density per ring, and here you see the results. So these are the points for the different rings. And you see that you would expect something smooth like this. Instead, you see that there is a peak in the galactocentric ring between 4 and 6 kiloparsec. So this is what is interesting from this plot is that it overlays also the OB stars distribution in galactocentric distance and also the supernova remnant. And you see that this peak is actually coinciding with the OB star peak. So this is connecting to the young stellar cluster that I was mentioning before. And the explanation for this excess is that the cosmic ray sea is enhanced by the fact that in this inner region of the galaxy, it's plenty of cosmic ray accelerators. So this is another result from another team, just that confirms the same concept. What is also striking is that as long as you move towards the galactic centers, the spectrum is also hardening. And this is very difficult to explain unless we assume an inhomogeneous diffuse factor. So this is something that is very recent and is still under discussion. So there are plenty of theoreticians that are trying to explain this hardening, and it looks like the most promising explanation is inhomogeneous diffuse coefficient. In the last years, we also get some data, not only in the high energies, but from the very high energies from LASO and another particle array detectors, which is called Tibet AES gamma. And so these data are still preliminary, but so theoreticians are already using them to try to prove that the inhomogeneous coefficient diffusion coefficients is better describing all the data, but it's clear that more data from the very high energy part will really help in defining and constraining the propagation models and also this kind of open questions. So far, as I said, they have been studying the diffuse emission. So the point was, let's try to understand if the cosmic ray density is the same in all our galaxy. And it was done by defining rings, galactocentric rings. Another way you can use to actually try to measure the cosmic ray density in different positions of the sky is to use what we call the passive molecular clouds. So you have super high density molecular clouds, so highly massive molecular clouds across your galaxy. And there, just because of the enhancement of the gas, then you can get enhanced gamma ray emission. And this is the case, for instance, this is one of the brightest close by molecular clouds, Orion A, where you see this is the Fermi-Lat map and this is the Planck map. You see that there is a good correlation between the dust opacity map and the gamma ray counts, which is what you would expect since what I have just said. So we are increasing the gas, and then these. So if the cosmic rays that are permeating that region illuminate that enhanced gas. So we also tried in the past to release, so now there was the publication of super detailed catalogs of molecular clouds across the galaxy, and we used this catalog to select the molecular clouds that can indeed be visible by Fermi-Lat. And how did we select them? By knowing that the flux of gamma rays depends only by this factor. So the mass of the molecular clouds and the distance from the molecular clouds. So these are what we call here the A parameters. And then we selected basically these around the tens of molecular clouds. So we performed the analysis in Fermi-Lat. And here you have the same profile as you saw before. So these are the points that I was showing before, but you also see the results from the passive molecular clouds that are confirming indeed that at distances above larger than 8 kiloparsec, basically we have the same density as in the solar system, close to the solar system, and the same is true also for the region really close to the galactic center. So this is Sagittarius B2, whereas there is an enhancement, although it's not, I mean, here the error bars are really large. So we would need more data to really confirm all these, but this hints that there is this enhanced also in the radius between 4 and 6, which can be related as well to the existence of cosmic ray accelerators. And here I stop. And basically, so the message I want to convey is that there was so the cosmic ray physics really improved and was advancing in the last years thanks to the gamma ray astronomy. But there is the need certainly for more precise measurements, for more sensitive measurements of different things. So both on the gamma ray emitting sources, on diffuse emission, but also on passive clouds. And all these will really help in constraining the propagation models and also in understanding which are the sources of the pevatrons, which is a kind of open questions that we have right now.
Okay, so well, thank you very much, Roberta, for the nice talk. And now let us open the floor for questions.
Yeah, I just missed on your talk the part about the prospects. When you are the representative of CTAO Observatory here, and it's the new generation instrument. So, how do you think the new surveys that are in principle planned to be performed in the galactic plane will impact in the current knowledge of both the diffuse gamma ray emission in the galactic plane and also regarding the accelerators and sites and production?
So thank you for the question. I didn't shoot because I mean it's not really possible to. There are not yet public results, and so it's to avoid chaos. But there are prospects. So from the point of view of the individual sources, I mean we will have two things. We will have what are now the bright sources, the known sources, with much more precision measurements. When I say precision measurement, it will be so spectral points with statistical error bars as low as 1–2%, but also a super control of the systematic uncertainty, which is what is really killing the killing factor in discriminating between different models. And another point is that the angular resolution, I mean, this is really visible when I show the angular resolution here of CTA with respect to what we have now and with what Hawk or Lazo can do. So here in terms of morphological study, you can really image the emission, the gamma ray emission, and try to correlate with the radio gas, which has a resolution which is much better than ours, and really look for detailed correlation. We could even look at the core. So if there is a difference in the energy density of the cosmic rays in the core of a cloud, and in the boundary of the cloud. So all these things, all this kind of study would need an excellent angular resolution, and right now it cannot be done, especially because Fermilat, which is on this kind of study, the king instrument at the moment has a resolution which is a point spread function, which is much larger than what CTAO, for instance, can have. In terms of diffuse, it's the same argument basically applies. I mean, for CTAO, it will be tougher than for LASO or SWGO to get the full sky diffuse emission, the full plane diffuse emission. But indeed, there, I mean, again, the angular resolution will be so good that you can really study large scale structure and correlate better with the gases. I didn't mention that one of the, I mean, whereas in the GeV energy range, the diffuse emission is really dominant. In the very high energy range, since the cosmic ray spectrum is very steep, the dominant component will be the sources. So what we are trying to address now, so there are ongoing studies, what's the fraction of unresolved sources to the diffuse emission, which should be more important than for the high energy range. And this can be done by basically by producing synthetic populations of source.
Just to point out, so this is also one of the keys on some of the things you said here, right? That CTAO will not be competitive with particle detectors. It is true that in terms of sensitivity, no, but whenever you want to study morphology of sources at tens of TeV or hundreds of TeV, it is actually the case, right? So
that's why we need the complementarity of the two. We need to know where to point at, and then with CTAO you will do the study and probably try. I mean, CTAO has the precision that will allow to really go into the physics of the object.
Well, thank you very much for the talk. Let me contextualize a little bit my question. I do a star formation, and when you mention the star formation, you ring the bells. And I wonder if there is any other system in CTAO, because now recently in the last few years, there has been many detection of variable sources in high mass young star objects. They are bursting, probably by accretion or by other things. The fact is that both in the radio regime, the flux can increase by sterile chances, and in the near infrared regime, which is the one that I'm more interested, can go more than even 2, 3, or 4 magnitudes in the K-band, 2 microns. I wonder, because they are monitoring sessions for these YSOs in the radio and in the infrared. So let's say that we observe a variable source. Could the CTAO point to it? Like
so CTAO has the capability of repositioning, so to follow up follow up on external alerts in 20 seconds, any point in the sky with the largest telescope, and within 90 seconds with the smallest one. So it means that, let's say within 1 minute, you will be able, even before with the large one, you will be able to point at the alert, the received alert. And if these kind of sources, these kind of alerts are already included in the BO alert system or GCN or whatever is the network that you use, they will be immediately received by CTAO, and if there is a proposal on these, CTAO will immediately point at the source.
And it is not implemented in this other system, because I'm not aware of those who we just apply for a DVD, for example, and say, look, we found this.
Yeah. Then you lose the, I mean, this will be the day after.
Right.
If you are, I mean, if you are all faster, I mean, you lose the possibility. Sure. I mean, how long are these bursts?
It could last for a few days, a few weeks, a few years. I mean,
so my suggestion is included in any of these existing networks, so that it will ease the follow-up of the, but it can be done through DDTs, or even there is the possibility, if you have an approved proposal on these kind of stars. So in the proposal, you can specify, I want an immediate reaction. So this requires that the observatory receive the alerts immediately, or you can request the interaction with the PI. So if the PI knows that the star is flaring, then he can, of course, the day after, he can contact the scheduling team, and the scheduling team will take care of including it in the scheduler the day after. So there is this possibility of interacting with the PIs, but you need to have the proposal approved.
Okay, well, thank you.
Yeah, going to that point, actually, are the policy for observing modes in CTAO already being discussed at the level of, okay, we will have a target of opportunity mode, like working in the way that you are describing right now already, or is that?
So the concept that I have described is in the science operation concept. Then if you are looking for the detailed workflows, then these some of them are there, some of them needs to be done. So I wouldn't say that we are ready with all the workflows, but the basic concept that you can have an interaction with the PI, that you can request for immediate reaction if there is a network, and then CTAO will commit to have this network connected, or the proposer commits to use your network. You can even, it's also foreseen the possibility that you can provide to the observatory a trigger criterion, so a piece of software that will be used to trigger your observation. So imagine that you want to monitor and you have proprietary data on radio, for instance, and you want to keep these proprietary, so you can have this kind of interaction with the observatory if approved by the TAC.
I think that maybe that at least a portion of the triggers he's interested in, that will have an optical signature for sure, might be already within the CTAO horizon due to the reactions to triggers sent, for instance, from LSST.
Yeah.
Yes, the brokers. So the problem becomes not to be filtered out for the ones that you are most interested in.
Yeah, we should definitely move to have the most automatic and certainly all the facilities are moving in that direction. So
I have also another comment that this element of transients that are interesting not only for extragalactic sources, but sometimes also for galactic, like Nova. So I think that stresses again the complementarity to the particle detectors, because when pointing, the pointed instruments like CTA are much more sensitive than the arrays, and so you have that when we look at the graph of the sensitivity cubes. This is a comparison that is fair for point-like sources, okay, but for steady sources, when you are looking at the minute scale, except for super extraordinary gamma ray bursts like it has been, the LASO or HAWK are much less sensitive than Cherenkov telescopes. So they are somehow differentiated also on the plane of time scale.
no, that's definitely true.
The probability that it happens overhead is larger if you're looking at they were very likely.
Yeah, they have been already very well.
They have been really. There was the brightest gamma ray burst happened just overhead of LASO. They detected
Just
the
after
very
the
high energy gamma ray emission of the brightest
And it was
gamma
really
ray
dark.
burst.
Right.
Anyway, so just to complete this, so the time scale of the things you are talking about are days, weeks, months, right?
Yeah,
So, I mean, not average, so this 20-second reaction we need for gamma ray bursts, they need to point there as soon as possible, but for these kind of things, the next day, for a nova and so on, is more than enough.
the way that we're doing now is that I get an email from the radio experts and say, there is a part in radio, I write a GPT and we send it, and in a few days, it gets approved, it gets observed in a few weeks, and
But-
still we're detecting stuff, so it's great.
No, but this can work, but then the suggestion would be with a proposal, you get it approved, and then you can have this interaction the
Right,
same
right.
way, but at least it's foreseen and it's much faster because the day after you can have
Sure.
already in the schedule.
We have developed like TAO, like target of opportunity proposal for GWST, you know, so I don't
Yeah.
see why not we can do the same
Exactly.
for.
More questions?
How good is the accuracy of position in the show?
The accuracy in position, so the source positioning is 30 arc second for the LSD and 15 for the others.
More questions? Okay, I have a couple of very quick ones. One, if you go to a slide 27, I think, where you were talking about molecular clouds illuminating this W44, no, back. No, over here. So you said here, so in the W44, it is very clear. Everything in yellow, I think, is the molecular cloud, right? Or what is it?
What is the yellow here? So this is
No,
gas in different
other- Is that all?
so W28. No,
This one.
yeah.
Yeah.
So
Everything,
okay, so this is once we subtracted
the contours, the yellow contours, or what?
the yellow contours, yes, is gas.
Is gas, right? So it is very clear that the cosmic rays are actually escaping over there.
But if you see here, I mean, it depends on the velocity. So this is like you have the line of sight of the gas now. Depends on the range in of
Then the color scale is CO or
CO.
okay.
And you see that for instance here you don't have anything there. It's not really clear. So it's not a super correlations as when you look at now. I don't have it, but when you look at this kind of
Yeah, so that was my question.
so here there is a clear correlation with the gas. So here, this B source is full of masers also. So it can be a star forming region.
Okay, so the green contours are the gas that there is around the supernova remnant.
No, the green contours here are the contours of the significance because this is excess map.
And then so where is the gas over there?
No, I don't have it.
Okay.
I'm telling you, so I can show it you later, but it's here the correlation is much more striking. Here the correlation, when you compute the significance of the correlation, this is not really significant.
Okay. Fine. And my second question was about the young supernova remnants. I think a couple of slides back. So escaping cosmic rays from young supernova remnants. No, back.
Supernova.
From young supernova remnants. So yeah, we're here. Yeah, fine. No, so well, my question is, so there is the theory that PV acceleration may be happening only in young supernova remnants. These cosmic rays may be escaping very early, and then in order to detect them, so what do we need to do? We need to search for young supernova remnants that have molecular clouds nearby that could be.
I mean, there is
this
this,
PV, because the PV they cool down very fast. They lose their
Exactly.
energy.
So there is you need supernova remnants. No, sorry, supernova explosions. Recent.
Okay.
First. We have these G1.6 plus something, so the one in the galactic center, plus the galactic center, which is 100.
Say doesn't work, for example.
Casei is 500 years.
But then the PEV cosmic rays.
I mean,
will
the
be
problem-
around.
Yeah, I mean, it's something that we can do with much more sensitivity, because you need to really dig into to have like flux maps. That's what you need, and then to establish the flux upper limits. Then, if you correlate with the gas, you can constrain if there is an emission from escaping cosmic rays. But there are sources better than Casei, like this G1, so the galactic center one, G1.6, and actually has looked at it and has set severe upper limits on the flux around the sources. I mean, this is point like, so up to 30 parsec, you're sure that there is no escaped emission. And there it's quite puzzling because, and for these, I mean, it would be good to look with CTA because then you can really try to see if you can first detect the source itself and then having a much more deeper.
And if you don't detect it, then the upper limits will be limiting these models that are predicting the shapes of PV particles.
Exactly.
Okay. Good. So are there any other questions? Okay, so then it's time for Roberta again.
And now you have the biscuits.
I didn't ask her her question.
Ah.
So